In the past few classes, we've been working with and trying to understand indefinite integrals. And when you're finding an indefinite integral, what you're doing is finding a family of functions whose derivative is what you're taking the integral of. Now, a definite integral is something that is a little different, but related in maybe an unexpected way. So this little object right here looks like regular old integral, but notice how there's an a and a b above and below the integral symbol. When you see those two numbers there, or sometimes they'll even be variables, that's an indication that we are going to be working with, instead of a indefinite integral, we have a definite integral. And a definite integral is defined as the signed area bounded by the curve and the x-axis. Now, if we take a look at this graph down here, what I mean by signed area is that any area that is above the x-axis will be considered positive. So let me highlight the positive area. All of this is going to be positive area between the curve and the x-axis. And then any area below the x-axis will be considered negative. So as we go forward and trying to understand these definite integrals, we're going to treat those areas a little differently. So what this notation basically means is that we are going to find the area in between these two boundaries. These two are going to be x values that are going to be partitions for our area. So the number on the bottom, that's going to be our lower bound. And the number on top will be our upper bound. So for example, on this first problem, it's asking for the definite integral of h of x, which is the graph shown, between -1 and 3. So if I draw those partitions out so that we can see -1 and 3, -1 is right here. Oh, let me get a pen instead of a highlighter. -1 is right here, and 3 is right here. And so what this is actually asking for is the area in between the curve, the x-axis, and those two boundaries. So we're looking for this area here. And you should recognize this shape and intuitively know how to find the area there. Right? We've got a rectangle, and we know how to find the area of a rectangle. It's simply base times height. And because this grid is scaled the way it is, where each line on the grid is just one unit, you can really just count up the squares there. But let's approach it as a base times height scenario. So the base being like this length right here times the height is going to be 4 times 3. And so this definite integral equals 12. Notice how the definite integral actually equals a number versus an indefinite integral, which is going to be like an equation, a function, and more broadly a family of functions because of the whole plus c thing. So let's take a look at b. b is asking for the area in between -2 and 0. So let me erase what I have up here. And actually, I'm going to leave, the one thing I do want to leave here is the area we just found, because we might need it later. Okay, this area is 12. And, I'm actually going to leave that highlighted, even though that's not what we're looking for in this next problem. I think it'll be worth just keeping it there because we might need to refer back to it later, and we don't want to have to recalculate it. So between -2 and 0 is going to be this little area right here. Okay, now these do overlap, so maybe it would make more sense to get rid of that 12 and split this up and say, okay, well, this little square here is going to be 9. This little rectangle is going to be that extra 3. And then the triangle that I have left over, well, we need to recall that the area of a triangle is 1/2 base times height. And so this is going to be 1/2 times 1 times 3. So we have really two shapes that we're going to find the total area from. You could treat this as a trapezoid, but I like to keep things as simple as possible here. We're looking for this area, and we know part of it's 3. But that area of the triangle is going to be 1/2 times 1 times 3. And then we'll add the area of that rectangle 3. So half of 3 is just 1.5, and 1.5 plus 3 is 4.5. So yeah, I'm going to write a little 1.5 in here so we remember that area of that little triangle is 1.5. That way we don't have to calculate it later. Okay, part C wants the area between -7 and 2. Okay, so that's between here and here. What it's asking for is the area between the curve and the x-axis. Oh. So looking for this area right here. You can get away with trying to find that area as a trapezoid. That's going to require that you remember the formula for area of a trapezoid, which really isn't that bad. It's just the same as a rectangle for the most part, just base times height. But the only catch is you have two different sized bases, so you average those two bases. So actually, we already know how to split this up into a rectangle and triangle. Let's look at the trapezoid formula. So this would be base times height, but the base is the average of the two bases. So notice how these two segments are of different length. One is 2, and the other one is 1, 2, 3, 4, 5. So the average of those would be like 5 plus 2 divided by 2. Okay, that's what I'm going to use as my quote-unquote base, what if I'm thinking about it like area of a rectangle, times the height, which in this case would be 3. So 7 plus 2 is, 5 plus 2 is 7. 7 divided by 2 is 3.5. 3.5 times 3 is going to be 10.5. Now, there's one other thing here, and that's that this area is actually below the x-axis. So any area that's below the x-axis, we are going to consider as negative area. Okay, so we're working with signed area here. So this one's going to be negative 10.5. Okay, let's move on to letter D. Clean this up a little bit before we go to the next one. So the next one says we want the area between 3 and 7. Okay, this one looks like it's going to be a little bit harder, but it shouldn't be too bad. I'm going to use a different color here. But I'm looking for the area between 3 and 7. So I'm looking for this shaded area right here. Now, that doesn't look like a rectangle or a triangle or really any shape that we're super familiar with. But what we do see is that little curve above it is a circle, or at least a semicircle, half of a circle. And so we could approach this a little differently by thinking about the rectangle between 3 and 7. So think about the area of this rectangle. And then if we subtract the area of this semicircle, what we'll be left with is that green area, which is what we want. So the strategy here is going to be to find the area of the rectangle, which is 3 times 4, or 12, and then subtract that area of the semicircle. Now, the area of a circle is pi r squared. So if it's just half of a circle, it would be half pi r squared, and in this case the r would be 2. So 3 times 4 is 12, and we've got 12 minus 2 squared is 4, divided by 2 is going to be 2, minus 2 pi. We can't simplify that at all, so we're just going to leave it as is. If you wanted you could put that in a calculator to get a rounded answer, but we're not really interested in rounding that. So yeah, this area is 12 minus 2 pi. Okay, so in other words, it's that rectangle minus all that circular area. So I'm going to bound this like this. Okay, and we've found the area of pretty much every piece here. The only one we haven't really found is this one over here. I don't know if we'll need it or not, but we can see that that's 3. Okay, let's look at E. Now, E is going from -7 all the way to 3. So we're going to be combining the area that we have down here, starting with -7 all the way to 3. We just have to be careful, and when we add these areas up, we want the area above the x-axis to be positive and the area below the x-axis to be negative. So I've already computed the area of each of these individual pieces, so we just need to add it all up. Negative 10.5 plus 1.5 plus 3 plus 9. So we have negative 10.5 plus, that would be 4.5 and 9. Negative 10.5 plus 4.5 is going to be negative 6, and negative 6 plus 9 is 3. Now, if you ever see absolute value bars around the function, just remember that absolute value of any number is just going to force it to be positive. So if you're finding if you're trying to find the value of a definite integral that has absolute value bars around the function, then you're just going to treat all of the area as though it's positive. So we're going to basically do what we just did, because the boundaries are the same. We're still going from negative 7 to 3. But that negative 10.5 here, we're going to actually treat as positive 10.5. So all the areas should be positive. So 10.5 plus 1.5 would be 12. Plus 3 plus 9 would be 12, and 12 is 24. Letter G. Let me zoom out a little bit. Sorry I have to zoom out so much, but I want you to be able to see that graph. It says h of x, we want the area between 2 and 2. All right, so if we want the area between 2 and 2, the lower bound is the same as the upper bound. So we really want the area of just like this little strip here. Not over here, but just that line. And a line segment has no area. If you try to use like base times height, the base would be 0. And so anytime you find you're trying to find a definite integral where the lower and upper bounds are the same, you're always just going to get 0. Now h looks a little weird. The lower bound is actually bigger than the upper bound. Now we can handle this, but what we need to do is we actually need to flip those boundaries. And to do that, we make the entire integral negative. So this is actually going to be equal to the opposite of the integral of h of x dx from negative 1 to 3. Now we've already evaluated the integral from negative 1 to 3. That was the first problem we did. We saw that it was 12. Right, so this is just going to equal negative 12. Letter I, we're going from negative 2 to 0 of f of x plus 3. Now, if you've got any kind of transformation like that, where you're adding or subtracting two different functions, you can split up the integral symbol. And actually, I've got a little typo there. That should be an h. We could split up the integral and integrate both of these functions separately. So this is going to equal the integral from negative 2 to 0 hx dx plus the integral from negative 2 to 0 of the function 3 dx. Now for that first integral, we've already calculated that. That was letter B over here. Right, we know it's 4.5 or 9/2 if you want to leave it as a fraction. But we don't have the value of this other integral. So we've got to think about how we're going to calculate that. So 3 is a constant. And if you want to think about what that graph looks like, it's just simply a horizontal line at 3. And what this is asking for is the area between negative 2 and 0. So it's just asking for this area right here. And so you can see that's just the area of a rectangle. It's a 2 by 3 rectangle. So the area of that rectangle is 6. And so the value of the entire definite integral is going to be 4.5 plus 6, which is 10.5. So there's kind of two special integrals integral rules here that you want to know, and we kind of went over them on G and H. But if you've got a definite integral where the boundaries are the same, notice here a and a are the same, then that definite integral will always equal 0. And also the second little special integral we have here is if the boundaries are backwards, and even if they're not, if it's for whatever reason, if it's convenient to do so, you can always swap those boundaries out. The only thing you have to do to sort of offset that is by negating the value of the definite integral. So you can flip these if you want. And in the case of thinking about this as area, most of the time it's advisable to go from smallest to biggest, the smaller number being on the bottom and the bigger number being on top. So if it's not that way, usually you want to flip that and negate the whole thing. So let's take a look at a couple quick examples here. Number 2 is giving us the value of 2 definite integrals. So we've got 2 of them right here. And yeah, so it's asking us a couple follow-up questions here. So the first one is, what's the integral from 3 to 1? So we know the integral from 1 to 3 is 4 of f of x. So to find the integral from 3 to 1, we just need to negate this integral and flip the boundaries. And so this will just equal -4. Now, B is really the only kind of tricky one here, but I think if we try to visualize it, it won't be as bad as you might think. So let's say, I don't know exactly what f of x is. It doesn't give us really any information except for the area under, these 2 intervals. But let's just say it looks something like this, okay? Now, we know that the area between, let's say, -2 is here and 3 is here. The area underneath that curve is 7, right? This whole area here is 7. And we're given that with the first piece of information. So I know the total area here is 7. But then they also tell me that the area between 1 and 3 is 4. So if I put 1 as a little number here, the area between 1 and 3 is 4. So if I know that the total area between -2 and 3 is 7, and I know that the area between 1 and 3 is 4, I can find the area between -2 and 1 by simply subtracting the 7 minus 4 and getting 3, right? Because this area has to add up to 7. Now, algebraically, the way that you would rewrite this is you would say that this integral equals the integral from -2 to 3, which is going to be like the total area under that, between -2 and 3, and then subtract the area between 1 and 3. So that's where we're going to get that 7 minus 4. I think conceptually you can see it a lot easier than trying to parse what I've just written there. 7 minus 4 is 3. Part C wants the integral between 1 and -2. Notice that 1 is actually bigger than -2, so we're going to want to rewrite this as the opposite of -2 to 1. And this integral is given, or is it given? Oh, we just found it in the last problem. Yeah, it's 3. So this will just be -3. The last one is asking for the area between 5 and 5. Now, there's no reference to 5 anywhere on any of those boundaries, but it doesn't really matter because anytime those boundaries are the same, this definite integral will equal 0. Here's a few other problems that are going to take advantage of some properties that I think you'll find pretty intuitive. So like, for example, part A, we've got the integral from 2 to 5 of 4 f of x. You can simply factor out the 4 and rewrite this as 4 times the integral of f of x from 2 to 5. All right, and then, yeah, this one's given right here. So we have 4 times 5, which is 20. So yeah, anytime you've got a constant factor inside your integral, you can always take it outside and just do the multiplication after you integrate. For b, we've got the integral of a sum of functions. And just like we did back on the front page when it was h of x plus 3, this one right here, we can split this up as well. And so we can rewrite this as the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of g of x dx, both of which are given. The first one equals 5. The second one equals negative 3, so I'm going to get 5 minus 3, which is 2. The next one is very similar to what we did up here. Okay, so we're going to treat it the same way. We're going to split it up and say we want the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 3 dx. Now to calculate that other one, it's not given. The first one's given, it's 5. But to get that other one, remember that we talked about this up here. We're really just finding the area of, didn't really like that. Oh, come on. Having some zooming issues here. But I'm looking right here. The integral of a constant function is just going to be the area of a simple rectangle, okay, where the base is determined. The base of the rectangle will be the difference between the boundaries. So going from 2 to 5, the base is going to be 3. And then the height is just whatever the value of the function is. So in this case, 3. So we have 5 plus 9 is 14. The last one is going to require that we flip the bounds. So this is going to equal the opposite of the integral from 2 to 5. And that integral from 2 to 5 of f of x is given. So this will be negative 5. All right, so that about wraps up our discussion on definite integrals. But before I let you go here, I want you to take a look at the difference between an indefinite integral and a definite integral. So a definite integral is where you do not have any boundaries on the top and the bottom of the integral. Okay, it's just going to have that integral symbol, and then you're going to have your function. And this is what we've been working with up until today. When you evaluate an indefinite integral, you're going to get a family of functions. You're just going to integrate like we have been. In this case, we'd get x squared plus 6x plus c, right? And that would be your answer. That's what the integral equals. Okay, this is a family of functions. So the indefinite integral, you get a family of functions. Okay, the process of integrating an indefinite integral is the process of antidifferentiating. You are finding the family of antiderivatives. Versus a definite integral, which will actually equal a number. Okay, so like if you had 2x plus 6, and let's see what that graph would look like. It's got a y-intercept of 6 and a slope of 2, so it's just going to kind of go up like that. And if we're trying to find the area between 1 and 3, trying to find this area right here, we're going to get a numerical value for that area. Now, there's a couple of different ways you could approach this area. You could approach it, as split it up and find the area of the rectangle and the triangle separately. But I'm just going to find the area of a trapezoid. So it's very similar to area of a rectangle. Okay, instead of doing base times height, the fact is we got two different bases here, right? Two different side lengths here. So we got to average those. So we're not going to have base here. We're going to have the average of the bases, which will be the value of the y value of these points right here. So I got to figure out what those are. Okay, 2 times 1 is 2 plus 6 is 8. And 2 times 3 is 6 plus 6 is 12. So my area here is going to be the average of those two numbers, 12 and 8 divided by 2. That's what I'm sort of thinking as my base. And then my height is the distance between the bases, which is 2. And that should be times, not plus. And so we get 20 divided by 2 is 10, and 10 times 2 is 20. So notice how you get a numerical value here. Now what I want you to start thinking about is these seem like two completely different objects, right? Like there doesn't really seem to be a very clear connection between the indefinite integral and the definite integral. But of course there is a connection, and we're going to talk about that connection a lot more in the next unit. So I'm going to leave you a little bit of a cliffhanger here on, what is going on. Like the indefinite integral is an equation where the definite integral is a number. How are these two things related? But I'm going to give you a little preview here. If I take this indefinite integral and I plug in 3 and 1 into x as like two separate instances of here. So what I mean by that is, like if I substitute in 3, I would get 3 squared plus 6 times 3 plus c, right? And if I plugged in 1, I would get 1 squared plus 6 times 1 plus c. And if I subtract those two numbers, watch what happens. I get 9 and 18 is 27. I get 1 and 6 is 7. 27 minus 7 equals 20. I'm going to leave it at that. I'm not going to really go into any more explanation, but I want you to just take a look at that, try to take it all in, and see that sure enough, there is some kind of connection here between the indefinite integral and the definite integral. So that's it for today's lesson. Y'all have a great day. I'll see you next time.